Hi, this is Craig Stocks here at Utah Desert Remote Observatories. You can find us online at utahdesertremote.com. And today I want to do a video that I've been wanting to do for some time, and that's to talk really just about color in astrophotography. A little bit about where it comes from, how we use it, and most importantly, how we can use Photoshop to get just the right color in our images. Let's talk a little bit first about just what the color is and where it comes from. And of course, color is very important in astrophotography. In a simple RGB color image, simple just plain color photo, it helps us to see what the target looks like, or at least it would look like if our eyes could see color in that dim of a light. Normally, even through a large telescope, most objects, looking through a telescope, you're not going to see the color. But because a camera can be more sensitive and it can take a long exposure, it can collect data and more photons and show color that we can't see by eye. That doesn't make it any less real. It's certainly real, just like an X-ray is real, even though you can't see through the skin. So in a simple color image, color is important. We can also augment that color with details taken through narrowband filters that focus on just very specific wavelengths of light. So in this case, these red splotchy areas, those are actually nebulae in this M81 galaxy millions of light years away. So that adds more information. If we do just a narrowband image, and here we are using the Hubble palette or the SHO Hubble palette. What that means is that we have color mapped sulfur as red, hydrogen as green, and oxygen as blue. And that's because sulfur is the most red of the colors and oxygen is the most blue of the colors. So this is somewhat a true color, but it's certainly enhanced beyond what we could see. But now we get even more information because we can see very clearly there's a lot of oxygen back here in this kind of background area, and a lot of sulfur in the foreground area, and a lot of hydrogen here in these yellow areas. So it's adding information to the image. And that's true of narrowband images in general. Most of them you're going to see are color mapped in this SHO color palette. This is the elephant trunk. Again, the same color mapping. This is an image you're probably familiar with from the James Webb Telescope. Now, the James Webb Telescope does all of its images in the infrared wavelengths of light. Infrared is more red than the reddest color we can see. So we don't have sensors in our eyes that can see infrared, even though there's a wide span of different wavelengths, just like there's different wavelengths of red, green, and blue. There are different wavelengths of infrared. And so what was done here is color mapping these different wavelengths of infrared and shifting them into the visible spectrum of red, green, and blue so that we can see the image. Again, if we can't see infrared, so without doing that, without using a camera and shifting the wavelengths into colors we can see, we wouldn't see anything. Another image from the James Webb, and in this case, color really imparts distance information, because the further away a galaxy is, and for the most part these are all galaxies in this deep field image, the more red the galaxy is, the further away it is, the more redshifted it is. Redshift just means it relates to the speed at which it's moving away from us. And we have found that the farther away something is, the faster it's moving. Therefore, the more redshifted. So in this image, the more red you see in the galaxy, the farther away it is. So it gives us some distance information. So digital color generally comes down to red, green, and blue. Digital sensors generally work in terms of red, green, and blue. And certainly our digital display devices, phones, monitors, tablets, and so forth, work in terms of red, green, and blue. Now, the reason red, green, and blue are used is because those are three primary colors. And in the general photography color wheel, we treat red, green, and blue as the primary colors. And the intermediate colors of yellow, magenta, and cyan are the combinations of the two primary colors. So, for instance, magenta is a combination of red and blue. Now, if you mix equal parts of red, green, and blue, you get white, or some neutral color that we would perceive as not having a specific color related to it. It would be gray, it could be dark gray, it could be light gray, it could be white. But the point is it doesn't have color. But again, you can see where the red and blue overlap, we get magenta. Where blue and green overlap, we get cyan. And where green and red overlap, we get yellow. And in fact, those are two different color models. Generally, when we're taking pictures with a color camera or we're displaying color images on a TV or monitor or phone or tablet, we're using RGB, where you basically start with a black background and then you add colored light through LEDs or lasers or some way of producing colored light. And the balance of red, green, and blue determines how bright it is and what color it is. And you can make, they say all the colors of the rainbow. It's more complicated than that, but you can basically make all different combinations of color, almost any color you want, just with the right mixture of red, green, and blue. I don't know if you've ever printed something, but when you print an image, you actually start with a white piece of paper. And you may have heard of CMYK printing. CMY is cyan, magenta, yellow, and then the K stands for black. And what happens there, when you mix equal parts of yellow, cyan, and magenta, the resulting color is black. So these are sometimes called subtractive colors, but the important thing to remember is when you're displaying something with light, such as on a monitor, you use red, green, and blue. When you're depositing ink on something, we're subtracting from the white. We use cyan, magenta, yellow, and sometimes black. Now, the way a color camera works, it has a color filter array in front of the sensor. Astronomy cameras come in both color versions and monochrome versions, and externally you wouldn't really see a difference. Almost any other camera that you use, whether it's in your phone or a mirrorless camera or a digital SLR, almost all of those are going to be color cameras, and they're going to have a color filter array, sometimes called a Bayer matrix array or a Bayer matrix. A monochrome camera, and particularly if you're looking at an astronomy camera, isn't going to have that color filter array. It's going to just have pixels without special color filters. Now, the way that color filter array works, if we look at the details on a color camera, each photo site has a little tiny color filter in front of it. And the most common is the Bayer matrix using red, green, and blue. And somewhat similar to the way our eyes work. Our eyes have red, green, and blue photo cells. Cameras have red, green, and blue photo sites, and it's a red, green, or blue because of the filter that's in front of that photo site. So each site, if you have a 20 megapixel camera, you have 20 megapixel or 20 million photo sites, but each one of those sites will record only red, green, or blue, depending on what color filter is in front of that particular pixel. So again, these are very, very small. The camera I use has 3.76 micron photo sites, so these color filters are that small. Now, as I said, each photo site only records the brightness of one color, either red, green, or blue. So for a given photo site, we know how much red fell on that photo site, but we don't know how much green or blue. And to make an RGB image, if you recall, we need all three colors. We need a red component, a green component, and a blue component. And it uses a process called debayering or demosaicing. And what it does is it looks at the surrounding pixels and estimates from the surrounding, if it's a red pixel, it looks at the surrounding green and blue, and interpolates how much green must be present at this site and how much blue must be present at this site, so that we can translate from a mosaic of just red, green, and blue into a full color RGB image, where now each photo site is fully described as a combination of red, green, and blue. This demosaicing can happen in your camera just as part of taking the picture, such as with your cell phone. It can happen in PixInsight as a discrete step of processing images that were taken with a color camera. Now, if you use a monochrome camera, as I mentioned, the monochrome camera doesn't have that color filter array. It just has pixels. So if we're using the 20 megapixel example, it just has 20 pixels, and each one of those pixels is just going to record the value of how much light is falling on that pixel. In order to get color, we use red, green, and blue filters that filter the entire sensor for just red, just green, and just blue. So you really, in this example, you wind up with 3 monochrome images. You wind up with an image representing all the red that was taken through a red filter, all the green that was taken through a green filter, and all of the blue that was taken through a blue filter. And then when you combine those into a single RGB image, you come up with that same or very similar color image. The difference, there's a little bit of increase in fidelity, and that's because every pixel in this image, we had an exact measurement of how much red, how much green, and how much blue was falling on each one of these pixels. We don't have to estimate from the surrounding photo sites how much of the other 2 colors might have been falling on this one site. So you get an increase in color fidelity, and also generally an increase in just sheer resolution, because you do lose some resolution through the demosaicing process. So with that, let's look at some practical applications of how this works. And first I'm going to jump into PixInsight. And just as an example, if you take a picture of the Orion Nebula through your telescope using a color camera, you get a color image. You may have to process it with the debayering set correctly, and correctly check the box for a CFA, which stands for color filter array. But the point is, you get a color image out of the camera. If you're taking a picture with a DSLR, generally you just get a color picture. And once you have a color picture, typically I would do additional processing with this. Most of the time, I'm especially interested in the RGB colors of the stars, because PixInsight has a tool called spectrophotometric color calibration that will calibrate the star colors to be very accurate compared to the true compositions of the stars. So it gives you very natural, very real, true-to-life colors in the stars. And generally to do that, I would run it through a process called Star Exterminator. And what that does, that removes the stars from the image, or at least all of the stars that it recognizes as being nice small stars, and then it gives you a separate image of just the stars. And then we can use this later to combine this star image with other information. Now, that's if you're using a color camera. What if you're using a monochrome camera? Well, instead of getting the color image like this, you get 3 monochrome images. You get a red monochrome image, a green monochrome image, and a blue monochrome image, where each one was taken through its respective filter. And typically you want to put these together into an RGB color image. And the way you would typically do that is through a tool called channel combination. And in channel combination, we have red, green, and blue channels available to us. And we just tell it that we want to put the red into the red channel, and we want green in the green channel, and we want blue in the blue channel. And then click the solid circle to execute this. And lo and behold, we get a color image where red, green, and blue were provided by these individual red, green, and blue monochrome images. And then we can process this the same way we did our color image. We can extract the stars and use the SPCC color calibration and basically treat it as a color image as if it had come from a color camera. It generally will have, as I mentioned, better color fidelity and a little bit better fine detail. So that takes care of if you're photographing with visible color and full color, sometimes called broadband color. What if you're photographing a narrowband image and you're really photographing through the very restrictive sulfur, hydrogen, and oxygen filters that capture just that very narrow band of color? So rather than capturing all the reds, for instance, which we did with this red filter, it captures just the very specific red color of just sulfur or of just hydrogen, or the specific blue-green color of just oxygen. Well, when you do that, just like here we got red, green, and blue monochrome images, instead you would get red, red, and red, or actually in this case cyan, representing the individual elements. So in this example, this is the Cygnus Wall, which is part of the North America Nebula. This is the data that was captured through an oxygen filter. This is the data captured through a hydrogen filter, and this is captured through the sulfur filter. And just like we did with the red, green, and blue, we can put these into channel combination and produce a color image. And as I mentioned, we want to use the chromatic order of the colors. So we want to use the most red for the red color, and that's going to be sulfur. So we'll choose the sulfur image for red. Hydrogen is actually red, but it's less red than sulfur. So we'll use hydrogen in the green channel. And oxygen is actually kind of a blue-green, but it's the most blue of the colors. So we'll put it into the blue channel. So now we're going to create an RGB image mapping sulfur, hydrogen, and oxygen as red, green, and blue. And when we hit the Apply Global, we get a color image. Now, because green is dominant, and it's dominant because hydrogen is a very dominant signal. In fact, hydrogen is by far the most abundant element in the whole universe. You typically will get very green images. And PixInsight has some tools such as SCNR, which we could use that to reduce the green. Let's reduce the green by something like 90% and apply that. And this will give us a little bit more natural looking color or more pleasing color, but we can really do better. For myself, I like working in Photoshop. And the reason is, for instance, I've combined these three layers into red, green, and blue, and then we removed some of the green using the SCNR tool. But each step, I'm actually recalculating and changing the pixels in this image. So you lose the ability to go backwards. That once I've taken this green out, if I decide 5 steps later that I took out too much, I don't have a way to put it back without undoing everything all the way back to this step, changing this step, and then redoing everything I did subsequently. 2 or 3 steps later, maybe not a big deal. 50 steps later, you don't want to have to go back and forth. And much like the old game of telephone where you whisper a secret from one person to the next, every time you make changes, you're actually changing those pixels and you're losing some of the fidelity, and certainly you're losing the ability to go backwards. So rather than doing this in PixInsight, I prefer to do it in Photoshop. And I'm going to talk about 3 specific ways of producing color in Photoshop. And so let's jump into Photoshop and start there. First, let's look at this RGB data. So we've got red, green, and blue, and we just looked at these same files in PixInsight. And if you remember, we use channel combination to combine the red, green, and blue. These are the same files, but Photoshop gives us a lot of ways to do most things. And there's lots of different ways to produce color out of 3 individual layers. And these are, in fact, layers. Each layer is one on top of the other. By default, layers are in normal blending mode. And in normal blending mode, you can't see through that layer. So I could turn this layer underneath off and on, and you don't see any difference because you can't see through. This is a color image, though, and we can confirm that 2 ways. One, if I look at the tab up here that represents this image, we can see it says it's an RGB image, RGB/8, which means it's 8-bit bit depth. I can also look at the image mode, and I can see that RGB color is checked. So this is actually an RGB image. And what that means is each one of these layers actually has all 3 colors in it. It's just that those 3 colors are always equal. In fact, if we look at the channels that make up that individual layer, we can see that there's a red, a green, and a blue, and they're all equal. And that's why this image looks gray, even though it's in a color workspace. So the easiest way to take a red, green, and blue, and typically I would do this step in PixInsight because I have the spectrophotometric color calibration. I'm doing it here as a demonstration. If we want to have red, green, and blue, I'm going to double click on this red layer to start with, to the right of the layer name, and the advanced blending options opens up. And for this layer, if you look here in the center, because this is an RGB image, I can see the channels red, green, and blue are all 3 enabled. Well, since this is red, I really only want red from this layer, so I'm just going to turn off green and blue. And then I'll do the same thing with the green. Since this is green, I'll turn off red and blue. And we're not seeing any changes because the top layer is the blue one. So let's double click on the blue layer. We want to turn off red and green. And we now have that same full color image where the red is coming from the red layer, the green is coming from the green layer, and the blue is coming from the blue layer. So that's a very quick, easy way of getting just red, just green, and just blue, and putting that into an RGB image. If I want to make some global adjustments, for instance, if I want to give this image more contrast, I could add a levels adjustment layer, and that's sitting on top of these 3 layers, and I can move the sliders in the properties panel. If I want to make this brighter or darker, if I want to increase the color saturation, I can add a hue saturation and increase the color depth or the color intensity. And all that is being done interactively, automatically. I haven't changed these layers at all. All I've done is change how they look by turning individual layers or individual channels off and on. So this is a very flexible way of color mapping. Now, as I mentioned with red, green, and blue, usually I want to do that in PixInsight where I can use the spectrophotometric color calibration to be sure that the stars are the right color. So for an RGB image, typically you would not do it this way. But what about a narrowband image? So if we look at this image of the Cygnus wall, and here we have basically the same information. We have the hydrogen, the oxygen, and the sulfur. And these are all loaded as individual layers, and then I did something called creating a layer group. So the hydrogen layer is actually within a layer group that I named hydrogen. And if I turn this layer group off, you can see it also turns off the layer within that group. But the important thing is I can add other things within this layer group, and for the most part, what happens in the layer group stays in the layer group. So that lets us individually fine-tune the sulfur, hydrogen, and oxygen. And so we want to add color, and then we want to control the color. Now we can use the same technique, and this is kind of technique number one. How do we color map an SHO image into sulfur, hydrogen, and oxygen being red, green, and blue? Well, we can do it the same way we did with this RGB. I can go to the sulfur layer, and now I'm actually at the layer group. Double click, and we'll turn off the red, or turn off green and blue so it's only red. We can go to the oxygen layer group. Likewise, turn off everything but blue. Click OK. So now we have red coming from sulfur, blue coming from hydrogen. And I don't see it because the hydrogen, I'm sorry, I think I said that wrong. Sulfur is red, oxygen is blue. Hydrogen we want to make green, and if I turn this off, you'll see that we actually have a red and blue image underneath here. The sulfur is red, oxygen we're adding just blue, and if we turn on hydrogen, and let's make it just green, now we have an SHO image where hydrogen is green, oxygen is blue, sulfur is red. And I can fine-tune these individually now. So for instance, if I want more red, if I want the sulfur to be more prominent, I can go into this layer group that contains the sulfur, and by clicking inside that layer group and adding a levels adjustment layer, I can increase the intensity of the red in the midtones and maybe darken the dark tones to give the red more intensity. Likewise, I can do the same thing with the oxygen. We can add some intensity, maybe take some out of the dark areas. Generally, then I use hydrogen as kind of the place where I'm going to balance all of the colors by balancing how much hydrogen is present. So something like that probably looks good. And just like we did before, we can add a global adjustment layer on top if we feel like we want to adjust the brightness of the image overall. And if we want to adjust the hue saturation, we can increase the saturation. We're using the same technique we did for the RGB. All we did was set our sulfur to be red, oxygen to green, and then, oxygen to blue, hydrogen to green. This is a good way, and it works reasonably well with this image. Some images, because the hydrogen is so bright and so overwhelming of the red and blue, you get a very green image, and it can be very difficult to try to rein that green back in. And it's also not the most flexible because we're choosing red, green, and blue, but we don't really have good options to say exactly what shade of red or exactly what shade of blue. So let's go to another approach to adding color. And to do that, I'm just going to make a copy of this image so that we have this one saved. So this is going to be RGB channel switches. So we'll save that, come back to the one we just worked on, and I'm just going to go back in time to that's too far back. So this is probably a reasonable place to start. So we've got our hydrogen just before, like before, our oxygen and our sulfur. So let's look at a different way of color mapping that's a little bit more flexible, and we'll get into this image a little bit later because this is a Photoshop file that was made available by Alyssa Pagan of the Space Telescope Science Institute. So this is the image that she produced for NASA to release last year as part of the James Webb launch of its first set of images. And this is the technique she used for color mapping these narrowband infrared wavelengths into something that we can see. And we'll look more into that in a little bit. But let's come back to this same image. What she has done, and we'll start with just one at a time. First, we have a solid black layer at the bottom. So in this case, this is just a solid fill color layer with pure black, and that's going to be kind of the background or the basis of the image. And then for each one of these layer groups, we'll start with the sulfur. I'm going to click inside the layer group, and I'm going to add a hue saturation adjustment layer. Now, you don't normally use this checkbox, but in this case we're going to click on the colorize. And what colorize does is it makes this whole layer whatever color is set on the hue slider. So I can use this hue slider and make this layer any color I want. And generally what you'll do is take the saturation slider all the way to the right, and then you'll take the lightness slider back part way, and then you set this hue slider to whatever hue you actually want. And since this is sulfur, we'll leave it red. And now the last thing I want to do is change the blending mode. And you won't see any difference at this point, but I'll change this from pass-through to screen. And you don't see any difference because we have this black background layer. And so what we're doing is adding red on top of the black background using a mathematical process called screening. And you don't necessarily need to know what the screening process is doing mathematically. It's adding this information to the black. So let's turn on our oxygen layer, and we'll do the same thing. We'll add a hue saturation, set colorize, and I'm going to take the slider all the way to the right for saturation, lightness part way back. And since this is oxygen, we want it to be blue or bluish. And we'll just start there. And keep in mind, this is a non-destructive workflow. We can come back and change any of these anytime we want. I'll go to the oxygen layer group, and I'll change that again to screen. Now we're seeing a color image. Now we're seeing sulfur is red, oxygen is blue-green. So this would be properly called an SOO image, where sulfur is red, oxygen is green and blue. Let's add the hydrogen. We'll add the hydrogen the same way. We'll add this hue saturation layer, click colorize, 100%, take it back part way. I'm going to change the blending mode to screen. Now I can adjust my color balance just by moving this hue slider on the hydrogen layer. If I want it to be more green, more cyan, more orangish, more yellow, it's very easy to move this slider back and forth and fine-tune the color that we want out of this image. If we feel like it's too strong, we can change the lightness up or down. And I can always come back to my hydrogen now if I want to make it a little bit more blue to bring out a little bit more of, I keep saying hydrogen, oxygen, to make, bring out more of that blue in the background. And again, we can add a adjustment. Anything above these layer groups is going to be a global adjustment, and so it will affect everything below it. If we want to fine-tune the brightness of the image, and if we want to increase the color saturation, and if we've saved the RGB stars, which I've done, we can put those stars back in just by turning on the stars layer and ensuring that it's in screen blending mode. And now we have an SHO image with RGB stars. I can save this as a large PSB, large format Photoshop document. I can close the file, close Photoshop, turn off my computer, come back next week, and decide, well, I really want to boost the oxygen a little bit. So I can boost that oxygen. I can change the color contribution of the oxygen if I want it to be even more blue. If we want to boost the red even more, again, we can do that. So you have all of this flexibility and we've not changed a single pixel in our original sulfur, hydrogen, and oxygen data. So it's an extremely flexible way of doing it. It lets you adjust the colors now, come back later and adjust them more. And it's much easier to have something like this to work with as your source document than something like we had in PixInsight, when it had all of this green and trying to figure out, well, how do I maintain everything but not have it look so green? So this is the way a lot of people do their color mapping, using a screen layer and the hue saturation in colorized blending mode for each layer. And I think I mentioned earlier that if we look at the this Carina Nebula image that Alyssa Pagan did, that's exactly how she did it. And she has made this Photoshop file available. I'll put a link in the description so that you can go watch the video where she describes her process and download her Photoshop file. And you can also download the individual files that she used to build this. So she has it divided into long wavelength and short wavelength. So this is the long, this is the short. And for instance, if we look at the 90 nanometer, so this is the 90 nanometer filter, so this would be the most red. And you can see all the things that she has done within that. Here's her original red image, and then she's done some noise reduction and some local adjustments using curves with a mask, hue saturation layer right here. So this is the color that she chose to map the data that came from the 90 nanometer wavelength in the infrared spectrum to make this image. So as I mentioned, you can download this data and do it yourself. And so in fact, I have done that. So this is my version of that image processed. I did a couple things differently. First of all, I separated the stars. If you look at her image, the stars were not separated from the source layers, so they were processed along with the rest of the data. I separated the stars, and that let me make the stars a little bit smaller, and I think I carried through probably a little bit more color, but mostly if you compare the size of the stars, these are much less large or a little bit less bloated because I was able to separate them out and process the stars independently from the nebula. And it also lets you turn those stars off if you're interested in a starless image. Let's look at the structure of my Photoshop file. I have the 6 layers over here. I have the ranging from the 420 nanometer, which is the most red, it's the longest wavelength, down to the, here's the 90 nanometer, and here's the 187. I did something different. Rather than using a hue saturation adjustment layer for each one of the layers, I picked 3 that were kind of in the middle and used the same technique I used over here of assigning red, green, and blue. My first 3 layers are specific red, green, and blue. So let's turn off, there's some global adjustments here. Let's turn off everything, and we'll just build it from the bottom up and see what's in this file. First, we have our red, and this is the longest wavelength. This is the 420 nanometer. And if I turn this layer group on, this is what it's contributing. So this is the red that it's contributing to the image. And then I took the 200 nanometer and mapped it to green, and that gives me this additional information. And then the third one is the 90 nanometer, and that's mapped to blue. And if I double click here, you'll see I did exactly the same thing I did with the Orion RGB. I just turned off red and green and have only blue turned on. So this gives me a kind of a foundation image of just red, green, and blue. But we have 6 colors we need to color map. So the intermediate colors are going to be orange, yellow, and green, where orange is between the red and green, yellow is up here between green and blue, and then cyan is going to be between blue and green. So if I turn on each one of these layers, here's the orange, for instance. Now in this case, I did use the same technique of a hue saturation adjustment layer, and that's the specific color of orange that I wound up with. We can turn on the yellow, and that adds a little bit more information. If I turn on the cyan, that adds that information. So now we have our full spectrum of colors from all 6 filters. This is just a whole bunch of global hue saturation levels, local adjustments, and that gets us to this point. This layer probably doesn't really do much in this image. All it does, it's an almost black layer set at 16, 16, 16 RGB, so it's a very dark neutral gray. And it's in lighten blending mode, so that there's nothing in this image that's any darker than that 16, 16, 16. So if there's anything that's getting close to a pure black, it just keeps it from being pure black. And then lastly, we have the stars on top. So when you turn all those layers on, there's the finished image in Photoshop with 6 layers, each one color mapped to a specific color based on the chromatic order of the most red to least red within the infrared color spectrum. So I covered quite a bit of ground here. I hope you found something useful in here. If nothing else, it's important, I think, to understand that when you see a picture from either on Facebook or from Hubble or from the James Webb or any one of these fancy telescopes, what you're seeing is not just a snapshot taken with that telescope. In fact, there are no color cameras on those telescopes. Everything is monochrome and photographed through filters, like I demonstrated with either red, green, blue, or sulfur, hydrogen, oxygen, or with specific nanometers pass filters in the infrared. And what it's capturing is just a grayscale image representing that color component within the field of view. And then it takes some sort of processing like this in order to impart color and impart meaning to those colors so that you can look at the image and you can understand what kind of elements are present where in the image, and sometimes even some depth information to know what's closer and what's farther away based on the color. So, hope you found this useful. If you have any questions, be sure to drop those in the comments and I'll try to answer them. I want to especially thank Alyssa, Pagan, and the Space Telescope Science Institute for making that information available. All of the data from the Hubble and the James Webb and really all of the NASA missions eventually falls into the public domain. It's sometimes embargoed for a while until the scientist who requested it has a chance to work with it. But eventually it's all made available, and you can go to the Space Telescope Science Institute website, download the different variations of the raw data, and work with it yourself. So with that, I hope you have a great day today and an even better night tonight under a clear, dark sky. Thanks.